During the 2025 Radio Dev Room at FOSDEM, we presented this MAX 2771 software-defined radio receiver dedicated to the analysis of global navigation satellite system signals, and discussed how this increased bandwidth allowed us to tackle new frequency bands beyond the legacy GPS L1, such as Galileo E1 or Galileo E5, with their increased bandwidth. And so analyzing these new signals requires that we learn how the modulation schemes operate. Indeed, the classical GPS is a binary phase shift keying with a chip rate of 123 megachips per second and a code length of 1023 chips, so that the full length of each code is 1 millisecond long. Whereas the E1 or E5 are using these binary offset carrier, these BOC modulation schemes, at the same chip rate but with a longer code, which already means that the longer code requires that we have an improved frequency offset compensation scheme, since here the code length of 1 millisecond only requires that we identify the frequency offset with a fraction of 1 kilohertz, inverse of 1 millisecond, while here we have inverse of 4 milliseconds, 250 hertz, so we must tune the frequency between the transmitter and receiver local oscillators to better than 250 hertz or even 10 hertz for this longer code. Now, if we have a quick look at the documentation related to the BOC modulation scheme, which is perfectly described in this document, whose copy is over here, we see that in this Galileo Open Service Signal interface description, we will find the documentation about how these modulations are introduced. So we have the low data rate data that is rebroadcast, which is mixed with chips of the pseudorandom sequence for code division multiple access. If we were in BPSK, we would just have a single mixer step, but because we're using BOC, we need to consider this additional mixing with an additional carrier. And these characteristics of these two carriers are described a bit below here, where we see that we have these B and C BOC modulation, where the frequency is at 123 megahertz and another frequency at 6 megahertz. So these two carriers are added to the original modulation here, and will introduce the null here, since we are running at 123 megachips per second and the frequency offset is 1.23 megahertz. This means that whereas GPS had the maximum power of BPSK modulation at the center frequency here, in Galileo the maximum power is offset by 123 megahertz and the null is located at 0 hertz. So this is what we want to investigate experimentally using GNU Radio, and we're going to address the signals that were collected by a B210, actually running at 6 megasample per second. We've recorded 1 second worth of data and saved them as 8-bit integers to try to mimic the low bit resolution of the MAX 2771. So these data are actually available on the IQ engine. If you go on the space signals over here, you will find these signals that were recorded in the GNSS L1 and E1. So it's recorded at 6 megasample per second, centered on the GPS L1 band, and it's a 6 megahertz long record. As always, since we save binary files in the data here, we must always record metadata, so in the SIGMF format, to remember what is the shape of the recording and how the data were collected. So if we have a look at the data that were collected, we have a meta file here, and this meta file includes information such as the encoding. It's a complex integer 8-bit, so it means interleaved 8-bit data, which are integers. The sampling rate was 6 megahertz. The carrier frequency doesn't matter because it was removed by the local oscillator. So this is the important aspect. We need to open complex integer 8-bit. So let's have a quick look at GNU Radio how we do this. So we take a file source and we ask GNU Radio to first of all read the file, which is over here. So that's our file that we saved, this guy here, and it's a data file that we need to open. Then we need to say that it's byte, so 8-bit data. We need to convert these interleaved 8-bit samples into complex data, and actually we can scale by a factor of 127 so that we go from the maximum to the minimum of an integer back to plus or minus 1. And we need to inform GNU Radio just to make sure that we have the same data rate than the recording. So this is our basic flowchart. As always, when there is no hardware in the loop, we need to throttle the data. So we throttle to make sure that we don't overload the processor, and we can start by looking quickly at the frequency sync just to check how these data look like. So we save this flowchart into something like this file here, and when we run this, we have our first analysis. So of course, GPS is something like, or GNSS is a 10 dB below terminal noise, so we hardly see a bump that would be related to the GPS signal. We can try to check whether we do have information collected on the signal by squaring to get rid of the BPSK modulation, so the phase being 0 pi. If we square, we have 0 2 pi, which means that we collect all the energy into a pure carrier instead of spreading the energy over the modulation speed bandwidth. So if we run this, actually the signal, since each bin of the FFT is wide enough, it collects of the noise over the bin width, so we need to increase the number of FFT sample to reduce the bin size and lower the noise per bin. And furthermore, we start seeing something over here. If we average enough, we're going to see the signals coming out. So these are the various BPSK modulated signals, each of one of them offset by the Doppler shift, and the mean offset is due to the local oscillator of the B210 being a little bit off. So probably we have something in our signal. We can actually also check if we, in the autocorrelation, if we have some repeated patterns, since the CDMA code will be repeated every code length. So we can actually, first of all, convert the stream into a vector so that we can perform the correlation in the Fourier domain. So we will need to remember that the Fourier transform of a correlation is the product of the Fourier transform of a signal times the Fourier transform of a reference code complex conjugate. So we first convert the stream to vector, and we're going to take this over a given length, which will be the Fourier transform length. Now, if we remember that the code length of Galileo is 4,000 chip long, so we're going to need 4092 times 6 megasample per second divided by the chip rate of 123 megachips per second. So we need something like 24,000 samples in our Fourier transform. So since a fast Fourier transform must be a power of 2, we're going to take something like 2 times, so that's 131,000, so that we have a few codes in our correlation. We're going to call this guy n, and we need to convert the stream to a vector length n. Then we take the Fourier transform of these guys here. Since we now have a vector, we're allowed, and this FFT must be performed on n sample long data and windowing. Since we wish to take the autocorrelation, we're going to first multiply conjugate with ourselves. So in this case, we don't need to take a second Fourier transform because the autocorrelation will look at our self-similarity. And the beauty of autocorrelation is that it will be irrelevant of the Doppler shift because the Doppler shift affects both reference and the measurement signal. Once we've completed the Fourier transform, we need to go back into the time domain. And once we're back into the time domain, we can go from vector to stream and display the results. So from vector to stream over sample of n data long, we take the magnitude of this guy because what we're interested in is the magnitude of the correlation, and finally we send this into a time sink. So the time sink will be our oscilloscope, so the time domain output, and this of course needs to be a real number with a length of n since we work with chunks of n data. If we play this flowchart and we autoscale over here, we're going to see the correlation repeat. So we need to remove the autoscale, and we see now the file is only 1 second long, whereas we are repeating the recording. So we see here at every millisecond, every 1000 microseconds, there is a pattern that is repeated, which is our GPS L1 code length. So now we've got two indications that we do have a signal that is relevant. We see that on the one hand, the squaring of a signal tells us that we have the right data, which are BPSK modulated, and we see on the autocorrelation that we have some useful information to look at. So first we can try to see what GPS signal we have, and if we look here, so we recorded some samples from the GPS L1. These are actually collected from this website where you have the various pseudo-random codes that were stored as mat files. So you can actually read each one of these mat files and save them as from your Octave interpreter, save them as 8-bit integers. So these are the data file. If we have a quick look, we can see that the data file are indeed -1 or +1 value. We already made sure that we had mean value of 0, and the content of these files are real integer 8-bit. So now it's not complex, it's a real integer 8-bit. From this GitHub website we collected this. So again, we ask to open the file, and this file is named, for example, L1CA, and it's the data file that we wish to read. So that's our L1CA file here. Now this guy was recorded at 6 megasample per second as indicated over here, whereas this code is only 1 sample per chip, so we need to resample the code. In order to resample the code, we can use this Octave function, which calculates a rational fraction that represents the ratio of 1 over the 6 megahertz over 123 megachips per second. And this rational fraction calculation takes the number we wish to represent and a funny argument, which is the number of characters in the string representing the ratio. And if we do this calculation, we see that we have something like a good representation of this ratio. So we have to interpolate by 88 and decimate by 15. So if we add a rational resampler over here, so in order to perform the rational resampling, we can only use float or complex numbers. So we interpolate by 88 and we decimate by 15. And so in order to do this calculation, we need to have a character to float, first of all. And we scale the values by 127. Remember, this is a division, not a multiplication ratio. Once we have a rational resampler, well, we do the exact same thing as we did earlier. So we take the Fourier transform, we cross-correlate, and we go back into the time domain. So we're going to use these guys to complete the cross-correlation as we did earlier. The only thing is, if we want to do this calculation, we need at some point to compensate for the frequency offset between the code and the data that were collected, either due to the local oscillator offset or due to the Doppler shift. And to perform this frequency correction, we need to put a frequency translating Fourier filter, which frequency shifts the values that are input. So this frequency translating Fourier will be tuned by a acute graphic interface range, which we call the frequency offset. Now we know that GPS can only vary considering its 1.57 gigahertz carrier frequency and the orbit of a satellite between minus 5 kilohertz and plus 5 kilohertz, but we take a bit of margin to account for possible frequency offset of the receiver local oscillator. So we tell the frequency translating Fourier that this is the frequency offset we want to introduce, and we want the output to be the input, so we take the identity as the taps. Now that we can shift the frequency of the received signal to compensate for Doppler and local oscillator differences, we're going to complete the code correlation. And so this time, instead of correlating for the autocorrelation, we're going to take this guy as the second input of a cross correlation. The rational resampler now requires that we manipulate real quantities, and the FFT will take a real input as well. We finalize the whole processing chain over here, and we can take the Qt time sync, auto scale is on, and we can run this guy to try to search for the presence of a code in the known code in the received signal. So here is our squared signal, here is the autocorrelation, and if we search for the frequency offset that allows energy to accumulate, here we see that at around 3.6 kilohertz we have the correlation peaks, and if we stop and look more closely, we see that these peaks at 1.8 and 2.8 milliseconds indeed repeat once every millisecond. So here we have an example of cross-correlating the GPS signal with the frequency shifted collected data, but our objective was to learn how to use Galileo signals. So if we do exactly the same thing we just did with GPS, except we want to run this on Galileo, we take the same processing chain, except that now we're gonna read the data from the Galileo signal. So if we look, we have the space vehicle number 16 data. So this is our correlation here with E1b number 16, and we need to add the BOC signal, and the BOC signal will be a multiplication between the code and the square wave at 123 megahertz, as we've just seen in the documentation, but sampled at 6 megahertz, which is our whole flowchart sampling frequency. So we take a signal over here. This signal source is at 123 megahertz. sampled at 6 megasamples per second. It's a square wave with an amplitude of 2 and an offset of 1, so that we go from +1 to -1. We're going to rearrange a little bit all these processing blocks so that we can make a difference between them. And finally, we can connect all these guys together. So this multiplication acts on real quantities. This square wave is also a real quantity, so we shift it to float. It's a square at 123 megahertz. And we can connect now the BOC signal that was generated between the code and the pseudorandom sequence code and the square wave. Finally, we must again take the output of the first correlation to correlate with the correct signal. And if we now run this guy here, we had earlier a frequency offset of something like 3.6 kilohertz, and now if we search for Galileo, well, we should be able to see something. So Galileo being a sharper peak, you have to be a bit more careful in finding the right frequency offset. So since I prepared a little bit, it's 2700. And this time we have these correlation peaks which are further away because they repeat every 4 milliseconds. So if we stop the simulation, so this is the windowing effect. So if we stop this guy here, stop, and we take the calculation, we have 16 milliseconds, we have 20 milliseconds, so Galileo is repeating every 4 milliseconds. And we can search, since I stopped the first chart, the peaks are staying here, and we see that at 3600 we have our GPS signal. Now we can repeat this calculation for more satellites, but I think you understand the principle that we can indeed get the BOC modulation working. And if I look at the final flowchart that I presented during the FOSDEM, now in this example we no longer run the pre-recorded sequence. This time we actually calculate on the fly, since GNU Radio allows you to run some Python block, and this Python block is a code generator that is actually running the code construction. This code construction was found, instead of using the MATLAB file, we used this repository where you actually find in the GNSS tools the various code generation. So on the one hand, you've got this code generation, which is this guy over here, which we are using on this code, which is the code that is being used here at the chip rate that we just seen and the chip length. And these sequences are the ones that are found in this string over here, so that we end up running on the fly the various codes for Galileo and for the GPS blocks over here. Thank you.